Hello, everyone. My name is Mohammad Almasri. I recently received my PhD from the University of Illinois at Urbana-Champaign and was advised by Professor Wen-mei. It's my pleasure to present our work, Parallel K-Clique Counting on GPUs. In this talk, I will give some background, the motivation behind this work, our solution to accelerate K-Clique counting on GPUs. Then I'll show some results and insights into our K-Clique counting implementations. So let's get started. So the K-Clique or K-vertex-clique is a fully connected subgraph of size K. The problem of K-clique counting is defined as follows. Given an unlabeled, unweighted graph G, the objective is to count all cliques of size K. So for example, here, if we have graph G and the task to find 4 cliques in graph G, so the idea is to to find them and count them in graph G, and here we could find 2 4 cliques A, B, C, D, and E, F, G, H in this graph. Finding cliques is fundamental to so many areas like social network analysis. Usually they need cliques to find overlapping communities in the social graphs, find the densest subgraphs, and so on. Also, it's used in bioinformatics, chemistry, finance, optimization, graph database, query knowledge networks, and so on. Usually K-cliques or counting cliques in these graphs of these areas help characterize and summarize these graphs, and sometimes usually also to compare or contrast between two graphs. Usually a common approach to K-clique counting is to construct and traverse a search tree for each vertex in the graph, and then find the K-cliques that contain that vertex that we started from. So for example, if we start from vertex A in the graph, and the task is to count and find the 4 cliques in the graph, we expand to the next level by moving to or going to the immediate neighbors of the root vertex we started with, which is A. Next, to find the third level, we need to do an operation called set intersection between the adjacency lists of the vertices matched in the level 1, which is A in this case, and the vertices of level 2 to find L3, or the vertices of level 3. Next, to find the 4th level vertices, and notice that we're searching for 4 cliques, so we need to expand up to 4 levels. We need also to do the same set intersection operation between the vertices matched in the level 3 and the vertices of level 3 itself, which is basically the intersection, the results of the intersection of level 1 and level 2. So every time you expand, you need to do this set intersection operation. So notice that each path of 4 vertices exactly is a candidate for clique. However, since the clique is asymmetric, the subgraph, we can find that there is only one unique 4 clique in this whole tree, which is A, B, C, D. Okay, so how to eliminate redundancy in clique problems? There are different ways. One of the prominent ways to do that is graph orientation, and this is done by taking the undirected graph and convert it or transform it into a directed version based on some criteria like the vertex ID, vertex degree, or the vertex degeneracy order in the graph. Once we have the directed version of the graph, we can do the same expansion operation from one level to another using the set intersection operation, and we stop exactly at the K value that we're looking for. And since we're looking here for or trying to find 4 cliques, we stop at level 4. Another advantages of this graph orientation approach that it reduces the vertices adjacency lists in general. like the overall, and this will improve the set intersection operation since it has to deal with smaller adjacency lists when it does the intersection. The second benefit, it reduces the maximum out degree, and as we will explain later, it has a direct relation with the memory consumption. So reducing the maximum out degree will reduce the memory consumption of the whole solution. Another way to eliminate redundancy is called pivoting, and this solution is inspired from the famous Bronker-Bosch maximal clique finding algorithm. And the philosophy of pivoting is to find largest cliques, then calculate or find the cliques or the smaller cliques that they contain. So for example, if we go back to our same graph, so now we are showing all the level 1, the vertices, which are the graph vertices themselves. Before we move to level 2 or expand to level 2, we choose a pivot vertex. Usually this pivot vertex has the highest degree or the highest number of common neighbors with its parents. So in this case, it's B. We eliminate all its neighbors since they will be reached by the pivot vertex in the subsequent levels, exactly as I'm showing in level 2. We keep choosing pivots and expand, and notice that even we are searching for 4 cliques, we reached to 5 cliques, and then we found the number of 4 cliques that can be part of 5 cliques based on this combinatorial equation. Also, we do the same for the the remaining branches in the tree, and then we find the unique 4 cliques in the graph. The formula and the way to eliminate redundancy are all explained in so much details in our paper. So I would advise, if you need more information, to go back to the paper and read about the pivoting approach and our GPU implementation for the pivoting approach as well. The advantages of pivoting, that it reduces the search space significantly, as I'm showing here, and in the slide as compared to the previous slide of graph orientation. However, there are some disadvantages of pivoting where, like, we need to do deeper exploration, and this will make the load balancing worse in parallel implementation. Also, the second disadvantage is that there are like fewer and deeper trees, which will like basically reduce the parallelism. The last one, as you saw, we did not convert the graph into directed version, so it requires an undirected version. And as I mentioned before, this will make the set intersection operation more expensive since it has to deal with very long adjacency lists. The last 2 disadvantages are already overcome by parallel solutions on the CPU, as I will explain later. There's another optimization that that's used since, as I mentioned before, we spend a significant amount of time performing the adjacency list intersection. Also, there are like so all the set operations can be also represented as a set intersection. So this is a very important and critical computation in the K-Clique counting application. So a common optimization in the CPU world is for the intersection operation is to shrink the size of the adjacency lists further by removing from the graph, and for each root node in the search tree, the vertices that will never be reached by that tree. So, and this is where we create the induced subgraph, and we use it through traversal instead of using the original graph. So here we show that if we start from a root vertex A, we can see that the adjacency lists of its neighbors like B and C and D will have some irrelevant vertices that they will never be reached by A. So so this is like irrelevant work and need to be removed. So before we start the traversal, we create this local induced subgraph, and we eliminate any element or any neighbor that will not be reached by the root A. So as you can see between the left adjacency lists and the right adjacency list. The right adjacency list is significant; they are significantly smaller, and they will make the set intersection operation less expensive and more and faster. So this is exactly what happens. We use this induced subgraph for all set intersections, but building the induced subgraph is expensive, and also you're introducing new extra space to your problem. And in CPU world, this is not a problem because there is an abundance of memory in the DRAM. But when we talk about GPUs, we need a way to deal with this extra space, and also to deal with the expensive time, like the build time also needs to be reduced or like mitigated somehow. Okay, with all this elimination redundancy and set intersection operation improvement and so on, still the traversal complexity is very high due to the exponential growth of the intermediate results we are generating and the number of cliques we find. So for example, here I'm showing a real world graph with 1.8 billion edges. And I'm showing here a log scale figure that shows the number of cliques we find as the clique size increases. So as you can see, this exponential growth will have high memory requirement, needs high computational complexity due to the exponential growth, and scaling to large cliques is really challenging. So we need a scalable solutions to deal with this exponential growth of the number of cliques for larger cliques. So existing parallel solutions, when we look through the literature, this computation is dominated by CPU or parallel CPU solutions. So in the CPU, you can find that graph orientation exists with vertices or edges are distributed across the CPU threads. Each thread builds a directed induced subgraph, and then it performs the sequential depth first search traversal, because CPUs are good with recursion due to the large steps that they support. Also, you could find recent work on pivoting, and exactly they start by graph orientation, and this is to solve the main limitations in the pivoting approach in general. So they start graph orientation to have to expose more parallelism at the beginning of the computation, and then the vertices will be distributed across threads. Each thread also builds an undirected induced subgraph. So this is where we mitigate the problem of using the undirected graph. Instead of using the undirected original graph, we only use a small version, which is the undirected induced subgraph, to improve the set intersection and localize it for the root node. And then again, the solution will perform a sequential depth first search traversal on the CPU. If you go through the literature, then you will find that there is no performant parallel solution specialized for K-Clique counting on GPU specifically. Also, when you look through the literature, you will find that there are existing GPU solutions for similar problems like subgraph matching, but they adopt the breadth first search traversal instead of BFS, and I'll explain in the next slide why this is the case. So fine-grained parallelization strategy on the GPU are all offered to deal with the explosive tree traversal on the GPUs. Usually they use the BFS to exploit more parallelism, as I mentioned before. Once they want to generate the next level in the BFS approach, usually it's divided into stages, and each stage is divided into GPU primitives, and each primitive translates into a kernel call. So there will be so many kernel calls happening between the to do the BFS on the GPU. So as we get exponentially growing intermediate levels, you will have higher execution times. These solutions cannot really scale with large patterns and graphs. Patterns can be cliques or any different shape in the subgraph matching problem, which is like a similar problem to K-Clique counting. The required memory is not known before starting the traversal, and this is a problem because sometimes you need to get back to the CPU to get more memory or reserve more memory or offload memory. And due to this, as your subgraph you're searching for grows larger, some solutions just go out of memory, or they iterate over subsets of intermediate results, and they will have more kernel, CPU, GPU data transfers, and kernel launches, and then we'll get into the loop of high execution times. So our solution here that we propose a hybrid approach between BFS and DFS. It's main BFS for just like the previous, initial levels, like first or second level, and then we use our DFS on the GPUs for both the graph orientation and pivoting approaches on the GPU. As we will show, our GPU solutions significantly outperform existing parallel CPU solutions for the K-Clique counting problem. Okay, so before we delve into our techniques or like our solutions, so due to the massive parallel hardware resources in the modern GPUs, so GPUs offering promising opportunities to accelerate the K-Clique counting for large graphs. However, to succeed in parallelizing the K-Clique counting on GPUs, we need to overcome some additional challenges that arise from the difference in hardware characteristics between CPU and GPU. Mainly the set intersection, exploiting fine-grained parallelism. The load imbalance on GPU is more problematic than it is for CPU, insufficient recursion support on the GPU, and definitely the limited memory capacity of the GPU compared to the very large RAM or DRAM capacity on the CPU. So here I'm showing all the techniques that we used to accelerate this problem, and all of them will help. These techniques are designed to operate using a single kernel call, where there is no memory transfer between CPU and GPU. There is no overhead of multiple kernel launches like BFS approaches. And also our memory requirement is pre-allocated and known before even we start the computation itself. In this presentation, we will highlight some of our techniques that helped us have an efficient implementation of K-Clique counting on GPUs. So I'll start with the two parallelization strategies. And within them, I will highlight some of the other techniques that are used within them. So if we have the same pattern and data graph, this is how we organize our computation. So we provide a vertex-centric approach where we assign a vertex to a thread block on the GPU, or an edge-centric, which is assigning an edge to a thread block. And why we use a thread block as a unit for the beginning of our computation, to be able to amortize the high cost of building the induced subgraph. So all the threads in the block will build the induced subgraph, and this will help us build it fast on the GPU. This is one thing. There is some contrast when you build induced subgraph in the vertex-centric and edge-centric, but edge-centric approach is more robust against load imbalance, and it has shorter adjacency lists because of the smaller induced subgraphs. The second aspect of using blocks to as a unit of the work division is all the threads in the block will share the same induced subgraph. So high cost is amortized by thread collaboration to build it, and also threads of the block will share it through the tree traversal. Some details of our implementation is the total number of thread blocks that we use is exactly the total number of blocks that can run simultaneously on the GPU. So our memory requirement is related to the number of simultaneous blocks that work at the same time, not to the number of vertices or the edges. And also each block will reuse the same pre-allocated space as it gets a new vertex or edge after it's finished with its current work. And usually we use a work stealing mechanism to get a new vertex or edge, as explained in our paper. So our contribution here that we start with BFS for the first level of the or second level of the tree. Threads will collaborate and share the induced subgraphs. All the memory is pre-allocated and reused by the concurrent blocks. The second feature that we have is called hierarchical parallelism. Still, the thread block has so many threads, so we divide the threads of the block into thread groups. So the natural choice is to divide them into warps of 32 threads, but in our solution, we leverage NVIDIA's independent thread scheduling to create groups smaller than a warp. And this will improve the resource utilization and improve latency hiding. So we provide two ways of work division within the block. In the three-level parallelization strategy, which we use for graph orientation, we assign a block, let's say, to a vertex or an edge, and then the subsequent level will be assigned to a group of threads. With this design, each group will do a depth-first search sequentially by its own and independently from other group. There will be a single stack for each group, and the threads of the group will collaborate for the set intersection operation. For pivoting, since we have to go deeper in the search tree and we need larger stack because of the high depth of the search tree, we assign, again, let's start by assigning a vertex to a block. All the threads of the block will go DFS sequentially, and we will have a single stack for the whole block, not for a whole group. The thread groups within the block will collaborate to find the pivot. So each group will take, let's say, a neighbor, find the total number or the degree or the common neighbors with the root, and then they all will vote for the pivot. So there are so many independent tasks that the groups has to do to find the pivot, and this is why the groups are just used to find the pivot in the two-level parallelization strategy. And our contribution here is the way we did the fine-grain division within the block to do DFS, and also using the support partitioning to improve latency hiding and resource utilization. Yeah, the last technique we want to talk about here is the binary encoding of induced subgraph, and this is really critical for the GPU because GPUs has less memory capacity, and there are some aspects of the GPU that we need to take care of when we do the set intersection. So the induced subgraph is transformed into a binary representation where 1 means the existence of a neighbor and 0 means the non-existence of a neighbors. And it's like a dense representation in bits instead of having this sparse representation of the induced subgraph. All the intermediate results for all the levels are also binary encoded, which will also reduce the memory significantly by bit encoding the elements. And the most important part is we now can use bitwise AND operation to do the set intersection, which is for GPU, it's important because there will be no control divergence and it will improve memory coalescing. And these are the critical aspects that will get the GPU high performance when we use the bitwise AND operations. So our contribution here that we observed the importance of binary encoding and induced subgraphs for clique problems on GPUs. These binary encoding induced subgraphs are dominated or used in the CPU versions of this problem, but this is the first solution that port these optimizations efficiently in a GPU and prove that they are really working and working efficiently. So for evaluation, we use V100 with 32 gigs of global memory. We use 5 real-world graphs from the SNAP dataset. We compare our solution with best and state-of-the-art CPU solutions. Our count is the best and the fastest solution for graph orientation, and Pivoter is the only pivot-based solution on the CPU, and we evaluated it on 60-thread Intel Xeon scalable processors with 240 gigs of main memory. So when we compare our best implementations for pivoting and graph orientation with the state-of-the-art, we can see that our implementations consistently and significantly outperform the CPU solutions with a geometric mean of 12, 19, 12, 6, and 19 for K equal 4, 7, and 10 respectively. Notice that also for a conferencer, Pivoter, it gets out of memory on 240 gigs of DRAM, while our solution doesn't go out of memory for all K values on 32 gigs of global memory GPU. When we compare between graph orientation and pivoting, the transition from graph orientation being fastest to pivoting being fastest happens around K equals 7. Also, we study the impact of parallelization, binary encoding, and like subword partitioning in general, and we compare it against a vertex-centric approach with just using induced subgraph without binary encoding. And we can see some insights here that for initial K values, it's recommended to use vertex-centric. And as K gets larger, we get better load balancing, and we move to the edge-centric. Binary encoding in general will give you a 2x speedup, which is like for all the K values that we show in this figure. Subword partitioning also will give you an additional 2x improvement in general. Another thing we did is load imbalance analysis between graph orientation and pivoting, between vertex-centric and edge-centric for different K values. And the load imbalance analysis is done by counting the ratio of 3 nodes visited per SM and compared it compare it to the average number of nodes visited per SM. So load imbalance is higher for pivoting than graph orientation, which is naturally understood because pivoting has to go deeper in the search trees. Also, load imbalance increases with K, again, because we have to go deeper, and then this will exacerbate the load imbalance as we go. But edge-centric, for different K values, pivoting or edge-centric seems to be a sufficient solution to improve load balancing for the K-Clique counting on the GPUs. And yeah, we have like more details on this in our paper. Also, we did some graph orientation or criteria analysis, and we here compared between using the undirected and using degree-based orientation and degeneracy-based orientation. And we can see the degeneracy achieves lower maximum out degree, but has higher pre-processing time. Graph orientation is favored when K is less than 7, and the degeneracy orientation is favored for K larger than 7. And we give some insights and more details on this in the paper. Pivoting approach, we always use degeneracy orientation because anyway, pivoting is faster than the graph orientation after K equals 7. So the cost of degeneracy is being amortized. So in conclusion, before this work, CPUs are deemed to be better for K-Clique counting, and there is no performant GPU solution found. We propose a paradigm shift from the conventional breadth-first traversal to a new hybrid tree traversal, where the GPUs are really treated as a processor and not a co-processor to do some primitives as for BFS solutions. The outcome of this work that we significantly outperform existing parallel CPU solutions. Our techniques and primitives are generalizable to any problem that involves explosive tree traversal. Lastly, we will open source our implementations, techniques, and primitives on GitHub for further improvement of the graph, K-Clique counting, and graph pattern mining in general. Yeah, these are the references, and thank you very much. I look forward to see you all in the presentation session, and would be happy to take all your questions. Thank you very much.